Okay, hello everyone. My name is Ryan Tumminello. I'm a rising senior at Hendrix College. I'm a chemistry major, and my project this summer has focused on quantifying NO2 emissions from a forest fire located in Sequoia National Park using airborne, ground, and satellite measurements. So to give you just a little bit of background on NO2, NO2 is a short-lived EPA-monitored air pollutant. It's a critical precursor to tropospheric ozone, as well as monitoring the levels of methane in the atmosphere and the OH radical. It has a variety of natural and anthropogenic sources, most notably high temperature combustion through cars, as most of you guys know. But my project focuses on the intersection between the two most contributing natural resources, being biomass burning and lightning flashes. It's reported that up to 15% of the global NOx budget is due to biomass burning, and while lightning is not very well understood, 20% of the tropospheric NO2 actually can come from lightning. So I'll be using the Schaeffer Fire as kind of my case study for this project. The Schaeffer Fire began on Saturday, June 24th, around 4:15 p.m. in southern Sequoia National Park. It's listed as a lightning-ignited forest fire and is to date burned about 16,000 acres and is actually still burning as of right now, only about 94% contained as of this morning. It's primarily consistent of forest and shrubs as its fuel type. Over the course of SARP, we actually were able to observe the fire 3 different times, twice using the King Air and once on board the Sherpa. So when I began this project, I was interested in first verifying and looking into whether or not the Schaeffer Fire was actually a lightning-ignited fire, which I began by looking at the approximate location of where we thought the fire was, circled here in red, and using the NOAA National Reflectivity Mosaic is what you see pictured on the right, which is basically just a model of where we could see storm cells at a given time. And so we see that there is a relatively intense storm cell located just east of the fire right here, about a half hour before the fire is reported to have begun. So I then was interested in the 3 main factors for why forest fires are frequently started, being the total number of flashes that occur, having a flash of a high enough peak magnitude to actually ignite a fire, and the overall flash rate. So I got all of my data from the Earth's network total lightning network, and I plotted all of the flashes of lightning on the June 24th, starting at midnight, all the way up to 5 p.m., about an hour after the fire supposedly had started. That's what you see plotted here. We saw about 15,000, give or take, flashes during this time. I then subset the data to only look at the small percentage that actually made contact with the ground, pictured here, and being satisfied by the 12-ish lightning strikes that could have actually ignited the fire, I then wanted to look at the general trends in the peak current of these flashes. So we see, starting at about 2 o'clock Pacific Standard Time, a general increase in the overall peak current magnitude. A higher peak current magnitude leads to a higher risk and a higher chance of actually igniting a forest fire, where we see the peak around 4:10, 4:15, give or take, followed by a dramatic drop-off with the storm leaving the area. So with all of this in mind, I then took kind of the last piece of information and calculated the flash rate by taking the information from that first graph that I showed you with all of the strikes on the map, and then sorted them based on time into individual bins to look at the general flash rate, because an increase in flash rate at a given time is indicative of an increase in storm severity, and thus an increase in the likelihood of actually seeing a fire being ignited. We see in the general area of where the fire started, the largest increase in flash rate at the time being about a half hour before the fire was ignited. So with all of this information, I wanted to estimate the amount of NO2 that was actually created from the lightning itself. And I want to take a moment to say that in the literature, estimations vary by an order of 2 magnitude because the observed observations and the lab results don't agree very well on lightning-created NO2. So with that in mind, I took an average value from the literature and estimated about 80,000 to 250,000 kilograms of NO2 being produced by just the lightning alone, which is equivalent to 1 million high-efficiency cars driving for about 30 to 90 miles. Or in other terms, if we took the entire population of 500,000 people in Fresno and made them drive all the way down to Bakersfield, that's the amount of NO2 that would have been produced. But as I said, I'm interested in the intersection between these two things, and NO2, the production from lightning from NO2 doesn't just end with the lightning strikes themselves. And over the past 15 years or so, we've seen about 3,000, give or take, fires in the southern Sequoia National Park where 5% of those were actually lightning ignited. So understanding the amount of NO2 produced from the fires themselves is extremely important, especially since most of these fires were small, like the Schaeffer Fire, on the day that we were able to observe it. So what I did is I used a empirical model to characterize the NO2 over the fire. Now I want to note that this model was originally designed for fires of significantly larger size than what I'm currently looking at. They reported the results in terms of a mass emission ratio, which is in grams of NO2 per second of fire burning. And they were able to do this by combining MODIS satellite data with OMI NO2 vertical columns, kind of like how you see pictured here on the right. What I did differently is I didn't want to use the OMI columns because we actually wouldn't have seen this fire from OMI with the NO2 being produced from it. We used the GeoTASO instead. And what you see here pictured on the left is the fire as viewed on the 26th, and on the right, the 27th. And I want to just take a moment to reiterate what Josh just said, is you can't look at this and think of this as a concentration, because these are slant columns, not vertical columns. These are in units of molecules per centimeter squared. So we do see a rather significant enhancement between these 2 days, and I hypothesize that this is because the fire probably doubled in size between these 2 measurements. So I combined the data that we got from the 26th with some MODIS information from the same MODIS fire product that the authors of the original paper used. So what you see here on the left is the size of the fire as identified by MODIS, and on the right is a unit of fire radiative power, which is basically just a unit of fire intensity, which is important here in a moment. But if you look on the left, this whole polygon is what MODIS was identifying as the size of the fire on the 26th, where if you take the area of that polygon, that comes out to be about 5,000 square acres, which we know is a vast overestimate based on the ground-based data. The fire didn't reach that size for at least another 8 or 9 days. So based on some back calculations that I did, which I believe that the fire should have roughly been at this time, and the lat-long coordinates, I think that this little blue square that I have identified here is actually the fire being about 255 acres on the 26th. And the rest of the polygon that you see there is actually just smoke being detected from the MODIS instrument. So my next step was to combine the GeoTASO and the MODIS information that I had gathered to calculate my own mass emission ratio for the fire. So we calculated one that was about 1.9 times 10 to the 4th grams of NO2 being produced per second of the fire burning, which is really high when it's compared to the previously reported results for fires of much larger size that consisted mostly of forest fire as their biofuel. I then realized that, okay, we probably had a comparison issue because I'm trying to compare slant columns where they were using the OMI NO2 vertical columns. So we needed to try to calculate a vertical column. And as Josh mentioned, the way that you do that is you just subtract your slant column by your air mass factor, which sounds really simple, but it turns out it's really complicated. Partially because calculating the air mass factor is really complicated due to the smoke that is present in the air. And we actually don't currently have a method to devise your air mass factor using the GeoTASO over a fire, because this is the first time that GeoTASO has ever been used to quantify emissions over a fire, or so I'm told. So what I did instead was the next best thing is I used the geometric AMF that GeoTASO provides, which basically just looks at the difference in the angle of the sun and where the instrument is measuring to calculate a rough AMF to then recalculate my mass emission ratio of 0.6 times 10 to the 4th grams produced per second. My next step was, okay, I was interested to see how sensitive is the calculated mass emission ratio based on the total AMF that you calculated. So I knew that the OMI satellite would, even though I wouldn't be able to see my fire on the day, would have calculated an AMF over this general region. So I then took the reported OMI AMF, accounting for the geometric differences between where OMI is and where we would have been observing from the GeoTASO, and I calculated an adjusted AMF of about 1.2, which is down from 2.9, I believe was the original one. And then recalculated my mass emission ratio using this to get a final answer of about 1.5 times 10 to the 4th grams per second, where you can see that's kind of somewhere right in the middle between the completely unadjusted slant column and the geometrically adjusted AMF value. So in conclusion, I found that these mass emission ratios are rather sensitive. So my kind of final results and conclusions is we found a significant amount of NO2 produced by both the lightning strikes and the fire. I estimate that roughly 20,000 kilograms of NO2 was produced by the fire just on the 26th. And I need you to keep in mind that this fire has been burning for another 30 days and is still currently burning right now. So it's probably far surpassed the amount of NO2 produced from just the lightning alone. I have found that this was a relatively successful first attempt at using GeoTASO to quantify the amount of NO2 over fires, which has really promising application on board tempo in the next coming years. And finally, that the mass emission ratios are relatively sensitive to the AMF value that you eventually calculate, and so a lot of care needs to be taken in developing the method to calculate air mass factors over fires using GeoTASO. Just like to take a brief moment to thank Dr. Sally Passetti, Laura Judd, and Jeff LaPierre, got that right? For really helping me kind of piecemeal this project together, as well as the rest of Sally's Pallies. And with that, I'll take any questions.